plus over minus.
If the emitter is holding still, then that's zero, so I don't care if you add or subtract it.
Sure. Okay. Okay.
Despite the implication from my pre-calculus textbook, positive zero and negative zero are the same number.
Yeah, I wasn't thinking that.
Yeah, that's okay. Sorry, it triggered something. There was an PSAT question that a friend and I both missed because of that pre-calculus textbook, where is positive zero the same number as negative zero, or do they just both have the same value? And the textbook implied that they're different numbers with the same value, which made a difference for this one question.
But
Sorry.
just the same number.
Pardon?
They're just the same number. Because
Are they?
like you can, like if you multiply something by negative zero, which is zero.
Yeah, well, it has the same effect. It looks and smells and tastes the same, but are
So
those
it's
the same
like a-
number, or are those two numbers that have the same value?
2 and 2, they're the same number.
See, I would contend that they're actually different numbers, but they have the exact same value.
I mean, yeah, they're two, like, they're literally two separate numbers,
Yeah.
but they're not like,
This one question hinged upon that concept.
what?
I wish I could remember the specifics of the question, but I just remember that my friend and I.
Okay,
Put it
yeah,
this way.
I guess they are two literally separate numbers, I guess, but why would you need negative zero? What would you need that for?
The pre-calculus problem.
Well, you could just use zero, right? If they're the same value, then.
The pre-calculus problem was we had to prove that negative zero was equal to positive zero. That was the,
Is there even a negative zero?
How do you prove that?
Like,
I forget how we did it. It was,
Like, I can prove 1 + 1 = 2, but I don't know how you can even prove that negative zero even exists.
can you prove that 1 + 1 = 2?
Yeah, there's a proof for it.
Yeah, it's a 100-page proof.
Yeah, it's a 100-page proof.
Okay,
But,
sorry.
I mean, like, I'm just like.
It can be done.
hypothetically, yes, it can be done. But
Yes.
I don't even know if negative zero even exists.
Okay. You know,
Cause I mean, I've never seen that in the textbook.
yeah. I was just wondering if somewhere online there's a copy of that problem. All right, anyway, we digress. Sorry, you triggered
Oh, you're good.
childhood scars.
Just a nice little break.
All right, I'm gonna show a video on the Doppler effect. So if you need to stretch your legs, go stretch your legs. I'm just gonna let the camera run. So if you need me to turn it off because you need to talk to me about something, you don't want the camera picking it up, just let me know, but I'm gonna just let it run. And let the fans all over the world just stare at the board for a couple minutes. That's not what I want. You know, I understand it doesn't cost me money to put stuff here, it doesn't cost anybody money, but the ads are just annoying. I got so spoiled. Oh, turn this on. Watching TV growing up, there'd be, you know, they'd break the show, there'd be a couple minutes of commercials, no problem at all, and now I get annoyed by a 15-second ad. Hopefully the fan will turn on soon.
So you remember when they only had 3 channels?
Yeah. Oh, we were living in a big city, we had 4. My wife had 2 on a good day. She was rural Tennessee. back in a little minute. All right, here we go. Apparently, oh, that's right, I muted this out.
The visual aid. So here's a thing that is in Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of the road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
There's never...
So, Doppler effect. Jumping back just a bit here. Have we talked about Tacoma arrows? Did I show the video? Tacoma arrows. More appropriate in the previous chapter, but I'll show it now. Famous bridge disaster of the 40s.
fundamental jobs of an engineer is to compare loading conditions to strengths. If the loads exceed the strengths, you know you've got a problem. Buildings and other structures face a huge variety of loading conditions, including floods, snow.
Not what I wanted. Although practical engineering are usually pretty good videos. So when they built the bridge, can you see it well enough?
Yeah.
I am going to kill the other light. Just.
It must have been Washington.
Yep. When they built it, they knew about the winds, and so they made the bridge flexible enough in order to be able to handle the winds. And there were a couple times they closed the bridge just because the winds were high and it was vibrating a bit too much. This is film from the fateful day.
That's from the 1940s.
What was that?
That's from the 1940s.
Yeah, this is 1940. There's a guy on the bridge also, and it's kind of difficult to see here. I think that's the guy right there. Looks a little bit, there's this dark break in the white of the road there. But that's the guy. Professor from the local university. I guess University of Washington.
That looks like a whole car.
What's that?
There's a whole car on the road too.
Yes, there is, and you can see the professor right there. Now, what I want to know is, you get halfway across the bridge and then you're going, you know what, it's safer for us to walk than to just gun it. I just curious about the circumstances. Notice also that along the line here in the middle, you have as close to a note as you're going to get. The middle is not vibrating as much as the sides are. And so the professor eventually starts walking off of it. He tries to stay in the middle as much as possible on the node. There it is.
That must be really bizarre.
wave motion gone wrong.
So they like know it was gonna collapse or something?
You know, it seems that way. I've been told that they've closed it several times before that because of vibrating too much. But I doubt if they had footage of every time they closed it, so it must have been worse than usual. I have questions about how bad that was compared to the other ones.
It must be really bizarre standing on a bridge doing that while it's wading back and forth, you know, like the ocean. That must be pretty bizarre to stand on.
Yeah, and there's also implication in some of the footage that they didn't necessarily show there. Farquhar was still actually a part of the bridge when it collapsed. He wasn't in the middle section, he was near the edge, but Farquharson, whatever his name is. But he managed to hold on to his pipe. That's the important thing. Now, the Tacoma Narrows, not only there's obviously wave motion going on there, but that actually has been used in several textbooks of an example of resonance, that if I take a slinky, it has a natural frequency to it, as you've seen in that lab. If my hand starts moving up and down with the same frequency, what's gonna happen?
I'm not gonna do anything.
All right, so we have speculation that nothing's gonna happen.
No, the slinky is gonna go quicker.
Faster.
All right, so we got to move faster.
I just do what Nick says and say it's nothing's gonna happen.
All right, so it's a 2-2 die and fight. All right, so it's going to get worse and worse. Those things have natural frequency. So if you have a driving force that's hitting basically the same frequency, then it will get exaggerated. There was a bridge in Richmond when we were crossing over the James River going to see my grandmother, where, because bridges have sections to them, and there's a little bump as you go along bridges, and so there was a bridge and our car would start to sort of oscillate up and down, and it was oscillating, it was basically bouncing up and down a little bit more by the time we got to the end of the bridge than when we started, just because it was hitting it just about the right place. Now, it wasn't enough to make the car fall apart. I've been told that there was actually a car design that did that fell apart when it went over a bridge because of that, but I've not found, that just seems to be urban legend right now.
It's like a trampoline.
Like a what?
Trampoline. If two people jump on a trampoline at the same time,
Oh,
one person will get
Yeah.
launched up way higher than the other person.
if you can coordinate that. I guess you've done that?
Yeah.
Okay,
It's, it happens if there's two people on a trampoline at the same time.
okay. All sorts of great stuff with wave motion. I was going somewhere, I lost it. Oh, so before we get back to Tacoma Narrows, there was when I was doing engineering courses at Duke, and one of the professors talked about there was a place downtown in downtown Durham that was losing customers, and they surveyed customers about why they left or why they didn't come back a second time, and they said, nothing against the store, except every time I went in there, it just